Assalamu alaikum wa rahmatullahi wa barakatuh. Good afternoon, boys. I hope everybody is doing well, inshallah. By the grace of Allah, everybody is healthy and okay. Today, we will be continuing the presentation that we were working on. The topic was the nature of matter, right? And mashallah, everybody is almost here. This is commendable that you guys are coming on time. Excellent job, boys. And we have the reader of the presentation. Hudhaifa is here. So we will give this mic to Hudhaifa. All right, Hudhaifa, would you like to read?
Yeah, I would read it.
Okay, that's the spirit, man.
Solids. It's taking a time to load it, I can't see. Alright, it's okay. The molecules in the solid are very close together and do not move very much.
So what do you mean by that?
Like they are so close to each other and they don't move very they rarely move. That's why they're stuck in one place. That's why they are always together.
All right, Hamza, we don't have to write this because this presentation is available on the canvas. You can download it from there. So what were we discussing? The molecules are, solid are very close to each other, and there is no, no space, but not enough space between them. It's just an analogy, but a bad analogy, if you would ask me. So let's go to the next slide. Let's go forward. What is this? Oops. Yes, Huzaifa, what is this? Huzaifa muted himself. Huzaifa, at least read 5 to 6 slides, then I'll change the reader. Give it to the care supervisor, inshallah. Muhammad Al Sharif and Umar, are you guys listening to music or to the lesson? Yes, Huzaifa, you have the mic. And he has disappeared. Okay, let's give the mic to Hamza.
Should I just read it?
If you want to add any point to it, yes, why not?
Right. Solids hold their own shape. Solids have weight. Solid takes up space.
What kind of solid is in the picture?
That picture, I think it's gold, but it's hard.
Gold bar.
And heavy.
Yes, hard and heavy, has some space, and takes up space. Okay, so let's check the next point.
Are packed tightly together, have very little energy. It cannot move or anything. They just stay put, exactly.
So who are tightly together?
What?
What is packed tightly together?
Solids, particles and solids.
Particles, good.
They mean all of molecules are just in the same place and barely moves.
Good.
Like they're very close together.
They can only vibrate, like they're having disco music, trance. So they can vibrate to and fro at their own place. So, yes, next slide, please.
Solids have a defined shape, have a defined volume. Molecules are held close together and there is very little movement between them.
Okay, so the solids have two properties.
Mister?
Yes, Huzaifa.
Can I read after Hamza?
Where were you when I was giving you the mic?
Oh yeah, I just had to go for I had to drink water because I was thirsty.
Okay, so as I mentioned earlier, the one who has mic will at least read out 6-7 slides. Then I'll shift the mic to somebody else. So Hudhaifa just disappeared again. Okay, so solids have two things in 2 points very important, two properties: definite shape, definite volume, which means that it cannot be changed. By definite, we means that it is something which is hard and fast, and it is intangible. It cannot be changed, right?
Yeah.
So looking into this, what is this?
That's ice, and it's solid. It's full of it's filled with water, and it's yeah.
Okay, so here's a question: why does this ice floats on water? It is solid. It should be sinking down.
What?
This question is for the whole class. Raise your hand if you know why this ice floats on water. And it says solid.
Because it's made out of water, but when you freeze the water, it turns ice.
Yes, it is a solid. Because
Yeah.
it also has oxygen, Masuri, buoyancy, and oxygen. No, that's not the right reason. And Saidi is raising a hand, so let's give mic to Saidi. Yes, Saidi.
Because the weight, yes, is less liter. It's less than the water weight.
But it became solid. It should be heavier than the water. So Saidi is halfway there. Halfway, you're right. Let's
The
say,
volume,
huh? Onion?
the volume,
The volume.
volume.
Now you are 70% there. Come on, think, you're almost there. You said it's 75%. Just one more word. The mass over volume, what is that? The volume is smaller than the water. That's going to make it heavier, Basuri. What is Saidi, mass over volume? What do we call that substance? What do we call that thing? If we divide the mass of the water over the volume of the water. Density, exactly.
Density.
Yes. So the density of the ice is less than the water. That makes it float. When the water freezes, it's the only thing on the universe that doesn't contract. It actually expands. And when it expands, its
Mr.
volume.
Also the wood. Right?
Yes, also the wood. So the volume becomes larger than the mass. So it becomes less dense than the water, so it floats on the water. So, okay, good job. So let's go to the next slide. Let's see, what do we have over here? Yes, Hamza.
Liquids do not have their own shape. They take the shape of its container. Example: water, juice, and syrup. How do liquids look and feel?
Yes, how do liquids look and feel? What kind of a question is this? How can a liquid feel? How do liquids feel? I think it's a vague question.
It's kind of hard to explain.
Okay, take your time.
Should I just read it? Should I
Anybody,
just read it?
anybody can explain how do liquid feel? The first thing that comes to my mind was like liquids do not have any feelings. They are non-living.
Yeah.
But when we touch a liquid, how does it feel? Strange question.
It feels moving. It feels very weird to the touch because it isn't hard as solid. It's very loose molecules.
All right. So they could be directing the question towards the two properties of the liquids, One is called cohesive and one is called adhesive. If we try to touch the water will be, sticking to our hands. If we take out the hand out of the water, our hand gets wet because some of the drops of the water will be attached with our skin. This is called adhesive property, that the molecules of the liquid likes to attach with the other substances. And then there is a mercury. If you put your hand inside the mercury and take it out, not a single drop is going to be on your hand because they are cohesive in their nature. Cohesive means they love their own type and they do not like to get attached to any other type. So they cling to each other instead of any other molecule or any other substance. So if you put your hand on into the mercury and take it out, it will be as dry as if it never touched any liquid.
Yes, mister, you unmuted me.
Yes, you were saying something when we were talking about how do liquids feel. It feels
Oh,
refreshing while taking a bath.
yeah.
All right, so let's see. Omar will read this slide.
I'm going to read this. The next slide.
Yes, please.
This one.
Yes, please.
Liquids take the shape of their container. Liquids have weight. Liquids also take up space.
So
Particles in liquid are loosely packed, have medium energy levels.
there's one point where I need to explain. They have medium energy level. That means that the kinetic energy of the molecules inside the liquid, they have little energy. They're actually sliding past over each other.
Liquids have an indefinite shape and have a definite volume. Atoms and molecules have more space between them than a solid does, but less than a gas. An example later is more fluid, called fluid.
So the liquids will not have a definite shape. Shape keeps on changing, and they have a definite volume which will not change. So the volume stays constant, but the shape is constantly changing. And Abdul Wahab, did you do Umrah? You shaved your head? Nod your head if it is yes. I think he's not with us. So let's go to the next slide. We have the liquid.
In a liquid, molecules are in constant motion.
What kind of constant motion?
I guess they keep changing as as a shape.
Yes, we call it random motion.
Random motion.
Yes, they don't have any pattern. They just keep on moving in a random direction. And we also call it the Brownian's movement because he was the first guy who actually discovered that these molecules are just randomly hitting each other. They do not have a specific pattern. So let's see.
Molecules are close together. Liquids are almost incompressible.
Yes, you can't compress the liquids. That means they have the definite volume. When you're trying to compress, that means you can decrease the volume, but no, the liquids have a definite volume which cannot be changed. Okay, let's give this to Huzaifa. Huzaifa is so happy to, always happy to read.
Yeah, I'll be really happy to read it.
So come on,
Okay.
mate, let's read
Liquid.
it.
The two key properties we need to describe are evaporation and its opposite, condensation. Add energy and break intermolecular bonds. Evaporation, condensation. Release energy and form intermolecular bonds.
All right, so Basudi has a very interesting question, and he's stating an example. He says, are there extreme conditions where liquids may be compressed? and, for example, at the core of some stars. So I didn't study much about the stars' structure or what is inside of them, but as far as I can recall, or study something about the sun, and everything is like in a gaseous state. So liquids, they already have no spaces between them. They might be at extreme condition. You can compress them something around like 0.01%. Yes, it might be possible, but depends on what kind of liquids we are looking at. For example, you might have seen that the liquid water, when mixed with the alcohol, they don't add up. You have half ml of water and you have half ml of uh, those, let's say 500 milliliters of water and 500 milliliters, half liter of each. When you add them up, it doesn't make up 1 liter. It goes around something 700, 750 ml. The reason why the alcohol molecules are smaller in size is they occupy the spaces between the water molecule. So you have to study the structure of the liquid, that whether when you are trying to decrease the temperature, they might decrease a little bit in their volume, but not by the pressure, but by the temperature. And if their molecules are arranged like water, water arranges itself in a way where the water and the neighboring molecules of the water, they start pushing away. So because of that pushing away, they arrange themselves at maximum distance, and that's why the water expands. So other liquids may decrease in size, in volume, and that could be on extreme level of temperature, that is negative. We're going to negative 50, negative 100, negative 200. And it could be with a lot of pressure on top of it as well. So let's come back to the Hudhaifa's slide. He says the two key properties we need to describe are evaporation and condensation. Evaporation, where the molecules are jumping off the surface, from the surface of the liquid, and they're going into the atmosphere. And the condensation is the opposite of the evaporation, that the molecule starts combining together and they start form the liquid. So one of them is making the gas and the other one is making the liquid, exactly opposite of each other. Okay, thank you, Hudhaifa. So who is on the mic? Everybody muted? Wow. So let's give this Abdul Wahab. Abdul Wahab, you have the mic.
Yes, Mister. Mister, yes.
Yes, would you like to read?
Of course, I know. Okay, gases. Gas is a matter that can that it's all around you and fills many kinds of things. For example, bubbles, balloons, and balls are filled with gas. Air is also a gas. Can you think of another example? Yes, Mister.
What is the example?
Oxygen.
It's in the air.
Yeah.
Any other example?
Carbon dioxide.
It's in the air.
Nitrogen in the balloon.
It's in the air. Nitrogen in the balloon?
Yeah.
Really?
Yeah, the one that fly. When you take the nitrogen, your voice change.
That's helium.
I mean helium, Mister.
Yes, you mean helium. So have you guys tried, what do you call, breathing in the helium and then talking in the squeaky voice?
Yeah, Mister. Your voice sounds like this. Hello, Mister.
Yes, the squeaky voice. So have you tried it?
Yeah, I tried it 2 times, Mister.
MashaAllah. So try to bring it in the class when we will inshallah meet up. We'll try to do this experiment.
Mister, I'm
And-
crazy doing it.
Okay, no, don't do everything. So Omar
I
was
love
raising a
to
hand.
explore, Mister. I love to do new things in my life.
Okay, so Omar has done it as well. So we'll put Omar and Abdul Wahab in
Hamza.
charge of this. So Omar
حمزة
Bukhari.
اكتب حمزة بخاري يعني طلع هوية كاتب كل ده الاسم.
No. So we are going back to the lesson. We'll plan this after the class. Okay, who's gonna read? Abdul Wahab, continue reading, please.
Okay, gases. Gas is spread out to fill the entire space given. Gases have weight, gases take up space.
So this is pretty much the common things that you might have done in the previous classes. Sorry.
I want to compare, Mister, I want to read, okay?
Yes, go on.
Particles in gases move freely, have lots of energy.
So when we say move freely, that means they do not have a pattern and they have the maximum energy. So the
Yeah.
last point.
Gases have a definite shape, have indefinite volume. Molecules are moving in random partners with different amounts of distance between the particles.
So the gases have indefinite shape, no definite shape, no definite volume. It can be increased or decreased. And molecules are moving in random patterns now with the different amounts of distance between the particles. So it's not like they keep social distancing. No, there's not 3 meters distance between each particle. They have various differences. Some may have a lot and some may have very little, and they keep on colliding. And even the collision is called, what do we call it? The ideal collision, in which we do not lose the energy and we do not lose the speed as well.
Mister, I close my mic.
You close your mic as you like. Mr. Watch my mashallah. Hudhaifa, this is not the right place to advertise your personal. Yes, Saidi, I'm giving you the mic. Okay. Yes, after the lessons.
Gases. The molecules in a gas have a lot of space between them and move freely.
Okay, so let's see this website. Can I have the access to the website? No. Hold on. Let me copy this. Let's open it up in the browser. Let's check out this link. And let's get surprised. Here's the link. Okay. To view this content, you need to install Java. Source code gas molecules. Okay. I don't have the Java. Built with processing. No, these are the guys who built it. So all right, let me try to install Java. Should have been on Flash. Okay, let's download Java. 1 minute. Agree. It's taking 1 minute time. Okay, we'll go to the presentation meanwhile. Okay. So can you guys see the presentation? We have chat. Yes, it has security plus. It's going to be obsolete by the December, inshallah. But still, for this these lessons, we use Flash animations because it's really helpful to let students understand the phenomena at time. So let me check again. It's going to take another minute. So you guys can see the presentation now. Okay, so let's complete one more slide and then we'll go to the presentation. We'll go to the animation. Okay. What is this? Steam. All right, who's going to read this? Muhammad Saidi, where are you?
Here.
Yes.
But what happens if you raise the temperature to super high levels, between 1000 Celsius and
I don't know what that number is. I think they missed one over here. 1,000,000,000,000 degrees Celsius. Will everything just be a gas? Well, the first question is, how much heat are you going to come up with to raise up the temperature about this much? Wow. This is next to impossible. But if it goes on to that temperature, yes, everything will become a gas, like a sun maybe. You'll have the Earth as a small star, right, Miss Yuri? What is the temperature of the star's inner core and the sun's inner core? How much temperature do we have over there? So meanwhile you people think about this, let's read that. Yes, Aidi.
If the gas is made up of particles which carry an electric charge, ionized particles, but the entire gas as a whole has no electric charge, and if the density is not too high, then we can get the fourth state of matter, plasma.
So here's the answer to the question. So we have gas. If the gases are made up of any gas, okay, that would be appropriate. Yes, we have a chat. How can the gas particles be ionized without carrying any? No, that's not what he's saying. He says if the gas is made up of particles, all right, particles which have electric charge on it, which are ionized. If they have electric charge, that means they're ionized. It could be positive, it could be negative. And this charge is created by losing or gaining of electrons. But on the other hand, if the entire gas has no electric charge, is not ionized, and the density is not too high, because if the density is too high, you're gonna go to the state towards the liquid. So if the density is not that high, then you will gonna get the fourth state of matter, which is the plasma. So it has to be on a very high temperature, which is up in the stars or sun. Let's see. We are discussing plasma now. Yes, Saidi.
Plasma. A plasma is an ionized gas. A plasma is a very good. A plasma is a very.
Yes, good conductor.
A plasma is a very good conductor of electricity and is affected by magnetic fields. Plasma-like gases have an indefinite shape and an indefinite volume.
Very good. Now, in the previous state, it was saying they shouldn't be ionized. Yes.
This after this lesson, I can watch this lesson or no?
After this lesson, you can watch this lesson.
Yeah, I want to see it again.
Or do you mean the recorded one?
Yeah, this one.
Yes, you can. But once I'll tell you where to find it, where to download it from.
Yeah, because I want to watch the lessons.
Okay, inshallah.
Thank you, bye.
Thank you. So where is our next contestant? Basuri, I'll give you the mic.
Yes.
Yes, would you like to read this slide?
Some places where plasmas are found. 1. Flames.
Really?
2. Lightning.
Very good.
3. Aurora.
Okay.
And 4. Neon lights.
The good life. Where is the next? What?
5. Stars. Stars make up 99% of the total matter in the universe. Therefore, 99% of everything that exists in the universe is in the plasma state. The sun is an example of a star in its plasma state. Clouds of gas and dust around stars.
We have
States
four,
of matter.
yes, four different diagrams. What do we see?
Um, it changes the amount of order in the particles. They
The
get
energy
more
level is
random.
increasing. The energy, the E plus E sign is showing that the energy is level is increasing. So each time you add some energy, it can change its state. Like the solids, when you start giving them the heat, they become liquids. If you keep them giving them more energy, it becomes gases. If you keep on providing more energy to gases, they become plasmas.
What if you keep providing more energy?
I don't know, we haven't reached to that point yet, but theoretically, people are working on it. You know, physicists, theoretical physicists, they are trying to discover it. So let's see. Yes, Vasuli, last 4 points.
Oh, solids, tightly packed in a regular pattern, vibrate but do not move from place to place. Liquid, close together with no regular arrangement, vibrate, move about, and slide past each other. Gas, well separated with no regular arrangement, vibrate and move freely at high speeds. Plasma has no definite volume or shape and is composed of electrical charged particles. But now, what happens if you lower the temperature way down to 100 nanodegrees above absolute zero? Will everything just be a frozen solid?
So the absolute zero is again a theoretical point at which the gases should become zero, the volumes should become zero. So if we have studied that, if we start decreasing the temperature of a gas, the distances between these particles will start become lesser and lesser, so that the volume will start decreasing. So imagine theoretically that you have started decreasing according to a graph, and you have reached to a point where the volume of the gas becomes zero. This temperature is called absolute zero, which is calculated to be minus 273 degrees Celsius. So if you go about that point, will everything just be a frozen solid? Let's see.
Mr. Water actually at high pressures will not be frozen.
No, not at high pressure, but temperature.
At low pressure, right?
Low pressure. No, it will be happy. It will stay as it is.
Mr.
Who is this?
Mr. Pussy muted. It's asked me to unmute.
You muted to what? I'm sorry. Can you repeat that again? Yes, Monsieur, you were saying.
Never mind.
Okay, so we have two scientists over here, Einstein and Boss. What did they say?
Not necessarily. In 1924, 82 years ago, two scientists, Albert Einstein and Satyendra Bose, predicted a fifth state of matter which would occur at very low temperatures. Einstein plus Bose.
So what did they predict the fifth state of matter would be?
Finally, in 1995, not too long ago, Wolfgang Ketterl and his team of graduate students discovered the fifth state of matter for the first time. The fifth state of matter, Bose-Einstein condensate.
So who are these people? I didn't get the 1995. Wolfgang Ketterle. I don't know where these guys graduated from. You should have mentioned that. So we heard about the fifth state, but these are the guys who actually figured it out. So they are saying that there is a fifth state of matter. Good to know. And we have, yes,
To really
please.
understand Bose-Einstein condensate, you need to know quantum physics.
True, agreed. And physics is not my cup of tea, especially quantum physics. So we'll just move on.
In 2002, Ketterle and two other scientists received the highest award in science for discovering Bose-Einstein condensate, the Nobel Prize.
Yes, everybody's clapping. Wow. So which year? Which year? Let me check the year. 2002. Good. This one?
In a Bose-Einstein condensate, atoms can no longer bounce around as individuals. Instead, they must all act in exactly the same way, and you can no longer tell them apart.
So they are like clothes. All of them are going to be exactly the same. That's like triplets down there. So we, okay, let's go to the next. Last 2 minutes. Yes, please.
Bose-Einstein condensation. The Big Peak happens when all the atoms act exactly the same way. We can't see Bose-Einstein condensation with our eyes because the atoms are too small.
Obviously, we can't see with the eyes. The big peak happens when all the atoms exactly the same way. So we'll try to watch a video on this. This is something new for me as well, because I haven't studied anything on this topic. So we'll watch a documentary on it and we'll try to learn something about it together. The next slide is
Energy and changes of state. A change of state is a change of a substance from one physical state to another. A change of state requires a loss or a gain of energy by a substance's particles.
so energy and changes of state. The change of state, like from solid to liquid or liquid to gas, right? From one physical state to another, and how much energy was lost while doing this or was gained by the system. We actually use the term system, which shows a closed system. It's an isolated thing. It could be any substance, but we isolate it from external temperature and the pressure. We are controlling all these things, and then we monitor that once we are changing the state, that how much energy is either lost or gained by that system, by these substance particles, right? So we are ending this session today at this point, and we'll start from here. I'll write down the slide number of it. So if you have any questions, please